Hello everyone. Let me start with a fun thought. Why do two sound waves coming from a guitar string sometimes sound louder and other times just fizzle out? Well, light waves do something similar, and that's the magic of interference. So, why does this happen? It all begins with the principle of superposition. Imagine two light waves passing through the same region. Their displacements simply add up algebraically. If we call the displacement of the first wave y1 and the second wave y2, then the total displacement y equals y1 plus y2. This superposition leads to varying brightness or intensity on a screen because light is a wave after all. When the waves line up perfectly, their phase difference, that's the offset between their waves' peaks and troughs, is an even multiple of 2 pi, which we write as 2n pi where n is an integer, and this creates constructive interference. That means the light waves boost each other, resulting in bright fringes. On the flip side, if their phase difference is an odd multiple of pi, or 2n plus 1 times pi, they cancel out partially or wholly, causing destructive interference. Dark fringes appear instead. The mathematical expression for resultant intensity is quite fascinating. It's the sum of the individual intensities I1 plus I2 plus twice the square root of the product of I1 and I2 times the cosine of the phase difference delta phi. Written out, I equals I1 plus I2 plus 2 root of I1 I2 times cosine delta phi. This formula lets us see the pattern of maxima and minima in brightness, the bright and dark interference fringes. But there's a catch. For all this to work perfectly, the waves must be coherent and monochromatic. Coherent means they maintain a constant phase difference over time, and monochromatic means they're all of one color or wavelength. Without these conditions, the interference pattern wouldn't sustain or might blur away. Imagine it like two dancers moving in sync versus to doing their own improvisation. Only the sync dancers create a perfect pattern for us to admire. In the diagram, picture waves overlapping in time, their amplitudes adding or subtracting, forming peaks that are twice as high, or valleys that flatten out, illustrating constructive and destructive interference beautifully. So, the principle of superposition is the foundation of wave optics, telling us how and why light waves interact to form these mesmerizing interference patterns. To observe interference, the two light sources must be coherent. That means they must have a constant phase difference and the same frequency. Temporal coherence is achieved when we use a monochromatic source, such as a laser or a lamp filtered through a single wavelength. Spatial coherence means that two interfering beams maintain a fixed path difference. In Young's double slit experiment, this is achieved by dividing a single wavefront. The light passes through two narrow slits, acting as two coherent sources derived from one parent source. When two independent lamps are used, their phase difference changes randomly over time, so no stable pattern is formed. A monochromatic light source shines on two narrow, closely spaced slits labeled S1 and S2. These slits act as coherent sources and project overlapping light waves onto a distant screen. At any point P on the screen, the path difference between the two waves is given by delta equals d sine theta, and for small angels, it can be approximated as delta equals d multiplied by k smiley divided by d, where d is the slit separation, x is the fringe position, and d is the distance between the slits and the screen. Constructive interference occurs when delta equals n lambda, and destructive interference occurs when delta equals to n plus 1 times lambda divided by 2. This results in bright and dark fringes appearing alternately on the screen. The distance between consecutive bright or dark fringes is called the fringe width, denoted by beta. It is given by the expression beta equals lambda multiplied by d divided by d. At the central bright fringe, the path difference is 0. At any position x on the screen, The light intensity is given by I equals 4I0 multiplied by cosine squared of pi dx divided by lambda d. This means that brightness varies smoothly across the screen and the total energy is conserved. It's only redistributed between bright and dark regions. According to Huygens' principle, every point on both slits acts as a secondary source of wavelets. These spherical wavelets spread out and overlap on the screen. Where the waves meet in phase, we get bright fringes. Where they meet out of phase, we get dark fringes. The time difference between the two waves reaching the screen is given by delta t equals d multiplied by k smiley divided by c multiplied by d, where c is the speed of light. The interference pattern is thus a direct consequence of coherent wavefronts overlapping. At any point P on the screen, the path difference is approximately delta equals d multiplied by k smiley divided by d. The corresponding phase difference is given by delta phi equals 2 pi divided by lambda multiplied by delta, which simplifies to delta phi equals 2 pi d k smiley divided by lambda d. The resultant amplitude is expressed as A equals to a naught multiplied by cosine of pi dx divided by lambda d. Since intensity is proportional to the square of amplitude, I equals a squared. Maximum intensity, that is 4I0, occurs at the central bright fringe, and minimum intensity, which is 0, occurs where the phase difference equals an odd multiple of pi. The appearance of the interference pattern depends on the wavelength, the slit separation, and the screen distance. Fringe width beta is directly proportional to wavelength lambda. Larger wavelengths produce wider fringes. Fringe width is inversely proportional to slit separation d, so smaller slit spacing gives wider fringes. And fringe width increases linearly with screen distance d, as given by beta equals lambda d divided by d. However, if d is made too large, the overall brightness decreases because the light spreads out more. Let's calculate the fringe width using our formula. We are given wavelength lambda equals 600 nanometers, which is 600 multiplied by 10 to the power negative 9 meters. Screen distance d equals 1.5 meters. Slit separation d equals 0.5 millimeters, which is 0.5 multiplied by 10 to the power negative 3 meters. Using the formula beta equals lambda multiplied by d divided by d, we get beta equals 600 multiplied by 10 to the power negative 9 multiplied by 1.5 divided by 0.5 multiplied by 10 to the power negative 3. This gives beta equals 1.8 times 10 to the power negative 3 meters, or simply 1.8 millimeters. So the distance between two consecutive bright fringes is 1.8 millimeters. The intensity at any point due to interference is given by I equals I1 plus I2 plus 2 times the square root of I1 multiplied by I2 multiplied by cosine of delta phi. Fringe width beta equals lambda d divided by d, and the phase difference delta phi equals 2 pi d k smiley divided by lambda d. The resultant amplitude is A equals to a naught cosine pi dx divided by lambda d, and intensity is I equals a squared. In Young's double slit experiment, coherent sources produce alternating bright and dark fringes. Fringe width increases with wavelength and screen distance but decreases with slit separation. There is no loss of energy, it's simply redistributed between regions of constructive and destructive interference. Thin film interference arises from multiple reflections, including a phase change on reflection from denser surfaces.